Welcome to another academy. In this video, we are going to discuss about orthogonality in inner product spaces. Already I have uploaded one video for inner product space. So the link is given in the description box. You can go through that video also. First, let's see the definition. If V is an inner product space and xy are any two vectors in V, then this x and y are said to be orthogonal if the inner product of xy is equal to 0. Okay. If x is orthogonal to y, then y is also orthogonal to x. Right? Because inner product of xy is equal to inner product of yx conjugate, isn't it? So, both are 0 at the same time. Therefore, whenever you say x is orthogonal to y, that implies y is orthogonal to x. And also, whenever x is orthogonal to y, alpha x, the scalar product alpha x is also orthogonal to y. Because inner product of alpha x y is equal to what? Alpha times inner product of x y, no? So, because of that, we say whenever x is orthogonal to y, the scalar product alpha x is orthogonal to y. And similarly, whenever two vectors x1 and x2 both are orthogonal to y, right? When two different vectors x1 and x2 both are orthogonal to y, then the sum of the vectors x1 plus x2 is also orthogonal to y. That is inner product of x1 plus x2 with y equal to 0. Right? And 0 is the only vector which is orthogonal to every vector in V. Right? This is like our usual product. In usual multiplication, what do we say? The multiplication of any number with 0 is equal to 0, no? The same thing is true for inner product also. The inner product of any non-zero vector with 0 is equal to 0. Therefore, what can we conclude? 0 is orthogonal to every vector in V. Okay, and this is the only vector with this property in any inner product space. Okay. Next, let's see what is an orthogonal set. See, orthogonal set means first you take an inner product space V and you take a subset S. Then the subset S is said to be orthogonal if any two vectors, arbitrarily if you take any two vectors from S, they will be orthogonal. Okay. So, otherwise how can we say any two vectors are mutually orthogonal? Any two vectors of S are mutually orthogonal. So, whatever pair of vectors you take from S, they will be orthogonal. Such kind of set is called what? Orthogonal set. Okay. Next one. Orthonormal set. See, orthogonal set means what? Any two vectors are mutually orthogonal. If along with that orthogonality, if the norm of each vector is equal to 1, already you know what is mean by norm. Okay, norm is nothing but inner product of the vector with itself is called what? Norm. So, along with orthogonal property, if the norm of each vector is equal to 1, norm is otherwise also called what? Length, isn't it? So, all these things we have discussed in the previous video itself. So, along with orthogonality, if norm of each vector is equal to 1, then the set S is said to be what? Orthonormal. Okay. Now, let's see some examples. See, I am taking Rn. In Rn, the standard basis is what? E1, E2, E3, etc. up to En, no? Right? In Rn, or it may be in Cn. That is nth dimension. Real numbers, nth dimension. Here it is complex numbers, nth dimension. For both of them, this E1, E2, etc. En is a standard basis. Okay, what is this E1? Number 1 in the first place, other places 0. Other coordinates are 0. E2 means what? 0, 1, 0, 0. That is 1 in the second place, otherwise 0. Right. Now, here you take this basis and you consider these vectors. If you take inner product of any two vectors, they will be equal to 0. Because, see, for standard inner product means what? Coordinate wise multiplication. First coordinate with first coordinate. 1 with 0, 0. Plus second with the second. 0 plus 0 into 1, 0. Plus etc. So, the product of the inner product of any two vectors will become equal to 0. So, therefore, it is an orthogonal. And what is norm of each vector? Norm of each vector is also equal to 1. Therefore, what do we conclude? This basis, the standard basis in Rn or Cn with respect to the standard inner product forms an orthonormal set. Okay, right. Now, let's see some results. See, suppose if we have an orthogonal set, v1 v2 etc vn in an inner product space, then that set will be linearly independent. Okay, you know what is linearly independent? That is, if you write the linear combination alpha 1 v1 plus alpha 2 v2 plus etc alpha n vn equal to 0, then each of the scalars alpha 1 alpha 2 etc alpha n all must be equal to 0. That is the definition for linearly independent. Otherwise, how can you say linearly independent? Here you are having n vectors. No, none of these vectors can be written as the linear combination of the remaining vectors. Okay, not even a single vector here can be written as a linear combination of the remaining vectors. That is called what? Linearly independent, right? So whatever orthogonal set you are taking in an inner product space, that will automatically becomes a linearly independent set. Okay, next one. See, here we have stated linearly independent, no? Now next we are going to find, see, this is a linearly independent set for vector space V. Now I am taking on vector V. Apart from this v1 v2 v3 etc vn, I am taking another vector V, and I am writing this V as a linear combination of these n vectors. Then the coefficient alphas can be found by using the formula inner product of v comma vk by norm vk square. Right? Can you understand? That is, first you take a orthogonal set. Orthogonal set means what? That will automatically become a linearly independent set. You take a vector from V which is different from these n vectors, and you write it as linear combination of these n vectors. Then the coefficients alpha 1 alpha 2 etc alpha n are there, no? That can be found out easily by using the formula inner product v vk by norm vk square. Okay, next one. Every finite dimensional inner product space has an orthonormal basis. Okay, so whatever finite dimensional inner product you take, definitely that will have some orthonormal basis. Next one, the orthonormal basis may not be readily available. See, already we have seen one example in Rn or Cn. This basis itself is an orthonormal basis, but this may not be easily available for all the finite dimensional vector spaces or finite dimensional inner product spaces. So what can we do in that case? There comes Gram-Schmidt orthogonalisation process. So this is a process with which what we are doing here is, we will be given with any basis for a finite dimensional inner product space. With that basis, we are going to develop an orthonormal basis. Okay, that's a procedure we are going to follow for obtaining an orthonormal basis. For that, what you have to take is CV1, V2, etc. Vn or any basis. From that, I am going to construct an orthonormal basis using W1, W2, etc. Wn. The first thing is, you have to take W1 equal to V1, and W2 is defined to be V2 minus inner product V2 W1 by norm W1 square by W1. This is nothing but, I have already stated, how to find the values of alphas. This formula only, this is what I have given here. Okay, right. And W3 is defined to be V3 minus inner product V3 with W1 by norm W1 square into W1 minus inner product V3 comma W2 by norm W2 square into W2, etc. So how will you write the general term? Wk plus 1 equal to Vk plus 1 minus summation j equal to 1 to k inner product Vk plus 1 with Wj by norm Wj square into Wj. Okay, in this way you can obtain all W's. This will be an orthogonal set only. It need not be an orthonormal set. From this you can write the orthonormal set by replacing all W's by W by norm W. Okay, so this is how we have to obtain the orthonormal basis for any given finite dimensional inner product space. Let's see some problems based on Gram-Schmidt orthogonalisation process. Obtain an orthonormal basis for V3 of R with standard inner product for the basis V1, V2, V3, where V1, V2, V3 are given here. See, this is not our standard basis. If you are given with the standard basis, no, it will be automatically becomes an orthonormal basis. But here this is not standard basis. Some other basis is given. From this, I am going to construct one orthonormal basis. So for that, what is the first step? Take W1 equal to V1 equal to the first vector. What is norm W1 square? With respect to the standard inner product, no. So norm W1 is nothing but what? 1 into 1 plus 0 into 0 plus 1 into 1 equal to 2. And let me find what is inner product of W1 with V2 and W1 with V3. Right? So inner product, what's the formula for standard inner product? Coordinate wise, that is first coordinate with first coordinate plus second coordinate with second coordinate plus third coordinate with third coordinate. So it will be 1 plus 0 plus 1 equal to 2. And inner product of W comma V3 is equal to 3 plus 0 plus 1 equal to 4. Okay, right? Next let's find what is W2. What's the formula for W2? W2 equal to W2 equal to V2 minus inner product V2 W1 by norm W1 square into W1. So V2 is what? 131 minus all these values I have already find out there. So 2 by 2 into 101. Right. Therefore, W2 equal to, this will be 1, no? So just you subtract. Coordinate wise subtraction. 1 minus 1 0, 3 minus 0 3, 1 minus 1 0. This is my W2. So whenever you find one vector here, you find its norm and you find its inner product with the remaining vectors. So the norm of this vector is equal to what? 0 into 0 plus 3 into 3 plus 0 into 0 equal to what? 9. And inner product of W2 with V3 equal to inner product of 0 3 0 with what? 3 2 1. This is my V3, no? So coordinate wise multiplication. 0 plus 3 2s are 6 plus 0 equal to 6. Now let me write what is W3. W3, the formula is V3 minus inner product V3 W1 by norm W1 square into W1 minus inner product V3 W2 by norm W2 square into W2. Let us substitute all the values. So 321 minus 4 by 2 into 101 minus 6 by 9 into 030. You simplify. So I obtained W3 equal to 101 and norm W3 square is equal to 2. So all the values we have obtained. So how will you write the orthonormal basis? W1 by norm W1, W2 by norm W2, W3 by norm W3. So this is the final answer. So if you want to write only the orthogonal basis, you can simply write W1, W2, W3. For writing orthonormal, you have to divide it by their respective norms. Okay, right. One more problem. Let V be the set of all polynomials of degree less than or equal to 2 together with 0 polynomial. Then V is a real inner product space with inner product defined by inner product of f with g equal to integral minus 1 to plus 1 f of x into g of x into dx. Starting with the basis 1x x square, obtain an orthonormal basis for V. So this is the basis given. So V1 equal 1, V2 equal to x and V3 equal to x square. This is the inner product defined. So with respect to this inner product, we have to find the orthonormal basis. Right. So let W1 equal to V1 equal to 1. Then norm W1 square equal to what? Inner product of W1 with itself. So what is the formula given here? First function into second function. Both are equal to 1. So 1 into 1 dx. So x within the limit minus 1 to 1. So it's equal to 2. So norm W1 square equal to 2. Next W2. What's the formula? V2 minus inner product V2 with W1 by norm W1 square into W1. So V2 is x minus, here directly I am applying without finding the term separately, directly I am finding out the values. Now norm W1 square is what? 2. So 1 by 2 into inner product of V2 W1. What's the formula? Integral minus 1 to 1. The first vector. What is the first vector? V2. V2 is what? X into W1 is what? 1 into dx. Here you see limit from minus 1 to plus 1 and here inside we are having odd function x. So the value of this integral is equal to 0. No need to do the integration. So directly you can write W2 equal to x. So norm W2 square is equal to what? Inner product of W2 with itself. So equal to integral minus 1 to 1 x into x dx, that is x square dx. So if you integrate x cube by 3 within the limits minus 1 to plus 1. So if you integrate, what's the answer? 2 by 3. This is norm W2 square. Next one is W3. W3 equal to V3 minus inner product V3 with W1 by norm W1 square into W1 minus inner product V3 with W2 by norm W2 square into W2. Substitute the values for V1, W1, W2 and V3. So W3 equal to x square minus 1 by 2 into inner product minus 1 to 1. V3 is what? X square. W1 is 1 only. So x square dx minus, this is 2 by 3, no? So 1 by 2 by 3 into integral minus 1 to 1. V3 is x square and W2 is x. Isn't it? So x cube dx into W2. W2 is x. Right. Now look at this integral. This is integration of odd function between minus 1 to plus 1. So the value of this integral will be 0. So the third term will not be there. Only the first two terms we have. So x square minus 1 by 2 into integration of this is what? X cube by 3 within the limit minus 1 to 1. So I obtained W3 as x square minus 1 by 3. Okay. Now the norm W3 square is equal to inner product of W3 with itself. So minus 1 to plus 1 x square minus 1 by 3 the whole square into dx. Let's expand the integration. See everything is even function. So instead of minus 1 to 1 I am replacing it as 2 times integral 0 to 1. Expand this. This is what? X power 4 plus 1 by 9 minus 2 by 3 x square into dx. So integrate and simplify. So I am getting norm W3 square equal to 8 by 45 or simply norm W3 equal to 2 root 2 by 3 root 5. So the orthonormal basis is given by W1 by norm W1, W2 by norm W2, W3 by norm W3. So this is the final solution. Okay, next one more concept we will see in this video, that is orthogonal complement. What do you mean by orthogonal complement? See, you take one inner product space and you take a subset S of V. Then, right, orthogonal complement is defined as the set of all vectors which are orthogonal to every vector of S. I have some collection S. If I have another collection such that every vector of S complement is orthogonal to S, then S complement is called what? Orthogonal complement. That is, S orthogonal complement is equal to set of all x belong to V such that inner product of xu equal to 0 for every u belong to S. That is, every element of S is orthogonal to every element of S perpendicular. Right? We can simply say it as S perpendicular or orthogonal complement of S. Now let's see some of the results. Now, orthogonal complement of any vector space is equal to 0 and orthogonal complement of 0 space is equal to V. Because we have already stated one property that 0 vector is orthogonal to every vector of V and it is the only vector with that property. So orthogonal complement of the vector space or the inner product space is equal to 0 and orthogonal complement of the 0 space is equal to V, entire V. Okay, now let's see another problem. S equal to set of all 3 tuples x0 0 where x belong to R, V3 of R with standard inner product. Then what is its orthogonal complement? Is equal to, see, in the first coordinate only you will be having some non-zero number, other remaining coordinates are 0. So for finding the orthogonal complement you should have what? Sorry, here it is not inner product, this is 3 tuple only, this is or ordinary brackets only. In set of all 3 tuples of the form 0, y, z. Then you will have these two are orthogonal because coordinate wise multiplication, no, so x into 0 0, 0 into y 0 plus 0 into z 0. See, this is nothing but the set of all points in the what? Where do you have this one? The set of all points in the x-axis. This is nothing but the set of all points in the YOZ plane, right? So the set of all points on the x-axis is in orthogonal complement with set of all points in the YOZ plane. Next one, if S is any subset of V, then orthogonal complement of S is a subspace of V. S need not be a subspace, but S orthogonal complement of S will be, definitely it will be a subspace of V. Next one, suppose if V is a finite dimensional vector, inner product space and W is a subspace. Here what I am taking, W is a subspace. Then V is the direct sum of W with its orthogonal complement. So direct sum means what? Every vector of V can be uniquely expressed as a vector of W plus a vector of W complement. Okay, so that is called a direct sum. Understand? If you take any vector V can be written as sum of, unique sum of a vector of W plus vector of W complement. Okay, this implies dimension of V equal to dimension of W plus dimension of W complement. Right. Next one, let V be a finite dimensional inner product space and W be a subspace. Then W complement, the whole complement is equal to W. See, this property you have to remember it correctly. This is true only when W is a subspace. If it is simply a subset, it is not a subspace means this property is not true. Okay, so you have to be careful with this property. So only when it is a subspace, we have W complement, the whole complement equal to W. Next property, V be an inner product space. If S1, S2 are subsets of V and S1 is contained in S2, that implies S2 complement is contained in S1 complement. Then another one property, if W1 and W2 are subspaces of V, then W1 plus W2 the whole complement equal to W1 complement intersection with W2 complement, and W1 intersection W2 complement equal to W1 complement plus W2 complement. Then another property is, if V is an inner product space and S is any subspace, then S complement equal to L of S complement. L of S is nothing but what? Span of the set S. Okay, so both the complements are equal to each other. Okay, that's all. Thank you.